In this work, we are proposing a few-shot scene adaptation crowd-counting approach using meta-learning. So this is joint work with my student Mahesh, Kumar, Mohammad, Hossain, and Mrigank, Rochan. So the idea is that we want to estimate the number of people in the image. So the common approach for solving this problem is given an image, you have a CNN model that estimates the density of the image so that the final count of the image can be obtained by just summing over the value in the density map. So most work in this area focus on supervised approach, but the problem is that this supervised approach typically require a large amount of training data which are hand annotated, so this is very expensive to get. And in particular, if you want to have a counting model for every camera scene, this is even more challenging. So in this problem, in this paper, what we are trying to do is we propose this few-shot adaptation approach. So during the training, we are going to assume that the training data are coming from many different scene cameras, and all the training images are labeled. Then during deployment, we are going to assume that we have a new camera, and for that new camera, we have a very small amount of labeled data. So the goal of the offline training is to learn a model parameter theta so that during adaptation, we can quickly adapt to the new camera scene. Okay. So here is an overview of our approach. So let's suppose we have an initial model parameter theta, and we have a particular scene that we see during training. What we are going to do is we are going to adapt the model parameter by a few gradient update, and we get an updated parameter called theta tilde. And then what we are going to do is we are going to use the remaining images from the training data to evaluate how good the adapted model theta tilde is. So essentially, we just define this loss function to measure how good the theta tilde is working on the rest of the image from this particular scene. Then during the meta training stage, what we are going to do is we are going to learn the model parameter theta so that we can do, the model parameter is doing reasonably well across all the scenes during the meta training. So we compared our approach with several different alternatives, such as just taking an off-the-shelf crowd counting model, or maybe just do a very simple fine-tuning in the target model. And we show that using the meta-learning approach, we can outperform all the alternatives. So basically, in our experiment, we tried on several different data sets, and we trained on some data set and test on other data set to ensure that our model is sort of generalizable. So in conclusion, in this paper, we propose this few-shot scene adaptation for crowd counting, and we propose a meta-learning approach for solving this problem, and we show that the meta-learning approach achieves better performance than all the other alternatives. So if you are interested, welcome to our poster.
Hello everyone, my name is Hyung Chang from the University of Birmingham. Today I'm representing my team to introduce the work point pose net for 60 object pose estimation. Our task is to estimate 60 pose of rigid object. The 60 pose here means the 60 rotation, 3D rotation and 3D translation relative to camera coordinate system. There are two contributions. One, our network can better utilize the object 3D local geometry information via 3D vector representation. Two, we verify the pose hypothesis with geometry constraint between estimated pose and depth observation of target object. This is our proposed architecture. Our architecture takes RGB and depth image as input. For RGB image, we use 2D detector to localize the object bounding box. Then we crop the corresponding depth region and transfer the cropped depth region to point cloud. We feed the point cloud to our proposed network. The network outputs 3D segmentation and 3D vectors, which pointing to 3D key points. Then we generate 3D key points hypothesis via these 3D vectors. We generate a position hypothesis for the key points from a point pair. For each point, our network outputs n vectors pointing to n key points. Then when we choose the first vector of both points in the point pair, we can get an intersection. We regard the intersection as the position hypothesis of the first key point. We generate the position hypothesis of the rest key points in the same way. Since we already know the 3D key point position in canonical frame, we can get pose hypothesis via Kapshi algorithm with 3D correspondences. Then we transform object model to the test scene via this pose hypothesis. We count the number of inliers of pose hypothesis via geometry constraint. When the shortest Euclidean distance between a point in the segmented point cloud and the transformed object model is less than a threshold, we regard it as an inlier. Then we choose the hypothesis that has maximum inlier count. Here is the comparison between using and without using our geometry constraint. The red boxes are generated by different pose hypotheses. The green is the mean box of the boxes. The blue is the best hypothesis. The black is the ground truth. From the result, we can see that by using our geometry constraint can better result. Here are some experimental results on line mode OCC dataset. You can see that even the target object are occluded by occluder, our method can still outperform. Thank you.
Hello, my name is Davis Rempe, and today I'll be presenting work done with my colleagues at Stanford on predicting the physical dynamics of unseen 3D objects. So in this work, we investigate the problem of learning to predict the 3D dynamics of a rigid object moving along a plane which has just been subjected to a force. As a result, the object acquires an initial velocity, and it slides along the plane until it comes to rest due to friction or it topples over. Our goal is then to accurately estimate the object's future trajectory by predicting the change in 3D position, rotation, velocity, and stability at each time step. We use the 3D shape of the object, represented as a point cloud, along with its initial velocities as input to our method. We assume that the object moves on a plane under standard gravity, friction and density are uniform and constant, and that the object eventually comes to rest or topples over. Predicting the dynamics of this problem is challenging because of complex 3D motions, for example, wobbling, or even toppling when the object becomes unstable. We propose a neural network to predict generalizable dynamics for 3D rigid objects. The change in state of an object depends both on its starting velocities, as well as properties determined by its shape, such as mass, inertia, and the contact surface. We use these observations to design a neural network architecture with two primary parts. The first is the shape processing branch, which takes in the object point cloud and aims to learn salient shape features that are crucial to making accurate predictions. The state prediction branch uses a recurrent neural network to predict the change in state at each time step based on the extracted shape feature and the input initial velocities. We use 3D simulation data to train our network on thousands of simulations of different object shapes using a physics engine. We simulate hundreds of household objects, for example ones from ShapeNet, such as bottles, mugs, speakers, and trash cans, to make our network generalized to shapes that were not seen during training. We show results of our method accurately predicting trajectories for a variety of object shapes. By training on a diverse set of primitive and ShapeNet objects, our method can generalize to unseen shapes both within and across object categories, as shown in all the examples here. Additionally, our method is capable of detecting when an object will topple over. We can also readily use our method to predict the dynamics of real-world objects. In the case here, our method is trained on a small set of sliding box data acquired using a motion capture system, but it's still capable of producing reasonable trajectories. Thank you, and please come visit our poster for more details.
Good afternoon, I'm Valentina Sanguinetti, and the title of the paper I'm going to present is Audiovisual Model Distillation Using Acoustic Images. Acoustic images are a new specialized audio data modality, and they are obtained combining the raw audio signals of an array of microphones through the beamforming algorithm. In our case, we have an optic acoustic device which is composed by a planar array with a webcam in the device center, which allows to obtain audio and video modalities aligned in space and in time. time. We use such data to obtain rich and robust audio features using distillation from both video and acoustic images modalities. We want to answer the question, does specialized data allow to learn more discriminant features for single microphone audio classification? To this purpose, we collected a multimodal dataset including 3 different modalities: RGB images, acoustic images, and raw audio signals. It consists of 14 actions performed by 9 subjects in 3 different scenarios with increasing noise conditions, which are an anechoic room, open space area, and a terrace outdoors. There are many audiovisual sequences which last a minimum 30 seconds each. The method we employed is the generalized distillation framework, which proposed to use the teacher-student approach to level aside information at training time, which in our case are both acoustic images or RGB images, which are given in input to a teacher network whose predictions are soft labels used together with hard labels to train student audio models, which have in input both time or frequency time representation of audio. Later, these models are trained with only 1 microphone information at testing time. We evaluate our audio models on 2 datasets, which are our dataset and decays. The results show that acoustic images distillation and RGB images distillation are able to improve accuracy respect of using only hard labels, and they obtain good results in cross-scenario conditions. Mostly we notice that acoustic images distillation is better to have more improvement. In fact, we also tested our audio models trained with acoustic images distillation on decays 2018, and we have good results if compared to those obtained from pre-trained models on Flickr SoundNet, which is a huge dataset if compared to ours. So the conclusion is that we collected a multimodal dataset which can be useful for further studies by the scientific community. We tried to transfer both from visual and acoustic images modalities to single channel audio models, and we are able to obtain more robust and powerful features. So if you want more information, come to the poster 5. Thank you.
So hello everyone, I'm going to talk today about the plugin networks model, which is a joint work from Tuplux AI. So in a scene classification, usually we have a pipeline where we have a CNN with an image as an input and the predicted labels as an output. But what if we have some additional information from some sensor? For instance, like we know that scene is indoor or outdoor, and we can call this additional information a partial evidence. Now there is a question how we can plug this information into already trained network. So we have like network like this, we call it base network, that is already trained on image, and we want to plug this additional information. So what we propose to do is to plug a set of small, fully connected neural networks that adapt activation of intermediate layers. So in this case, we can change the behavior of the base network. We don't need to train a base model from scratch, and the inference phase is almost as quick as for the base network. So here we have the example of inference. So we have the input, which is a park scene, but the base network classified it incorrectly as a river. So when we have like additional information that scene is man-made, our plugin network changes the intermediate activations of the network and corrects the output. So this was the inference phase. For the training, we used the original loss that was for the original task, and we backpropagate the error through the base network, but we don't update its weights. And then we backpropagate to the plugin networks where we update our weights. So in this way, we modify only our plugin network. And we show that we need only 20% of original training data. What is interesting that our plugin network clusters the activations of base network based on partial evidence, which is interesting because the network was not trained on that task. Our method is as fast as a base network and much faster than other competitors from the methods that use partial evidence, and we achieve state-of-the-art results comparing to other methods that utilize partial evidence. Here are some qualitative results. Here we have like the example where base network classifies a parking lot as a sound recording chamber, and here we have the example where our plugin network was used in a semantic segmentation, and we showed that plugin network helps with the label consistency, and also the objects are better filled with the correct pixel classes. So for more, please visit us at the poster number 8. And thank you very much. See you there.
Hello everybody, my name is Bertrand Luison and I come from a French AI and computer vision laboratory of a public research institute named the CIA List. I will present you today Calypso, that stands for classifying all interacting pairs in a single shot. This is an interaction classifier developed by Sana Shafik, Astrid Orsesi, Romaric Digier and myself. So, what is at stake here is to find all the action and or interaction that the people are performing in the scene. That is to say, enumerate a list of triplets, subject, verb, and target. For example, in the right image, you want to say that this person is using the laptop in the blue box while being sit on the chair in the cyan box. Yeah. So, what are the main challenges of such a detection? First, it implies a high semantic contextual understanding of the complete scene. You have to look specifically on the potential link between a person and an object, analyzing precisely the context and to see if there is an interaction link or not. Additionally, the number of potential interaction may explode as it is equal to the number of persons times the number of objects in the scene. This may become a serious time processing issue, especially for the end scene. Finally, you need to qualify the interaction type. For example, what is the fine-grained difference between holding a suitcase, carrying a suitcase, being sit on a suitcase, riding a suitcase? That's quite a tough problem. You have here some qualitative result of our method. Calypso estimates densely over the scene different features to determine existence and properties of interaction link between any potential person-object couple in the image. Readout couple are then enumerated at inference time thanks to an object detector to choose. When applied on videos, results are pretty faithful to the reality. And contrary to other state-of-the-art method, each frame of this video is processed in a constant time, whatever the number of objects present in the scene is. So thank you for your attention. You're welcome to come and meet me at our poster for more detail and discussion about interaction detection. Thank you.
Good afternoon, my name is Vineet Balasubramanian from the Indian Institute of Technology, Hyderabad, and this is joint work with the student Harshita, and the paper is titled A Little Fog for a Large Turn, Relevant to Autonomous Navigation Models. So, autonomous navigation models typically use data collected for ideal sunny weather conditions, and as you can see on all these news reports, they unfortunately do not work well for fog and other conditions. So just to demonstrate this, when you take a state-of-the-art network, PilotNet, it uses the same scene under different weather conditions. The predictions differ by nearly 1 radian, almost 60 degrees. This shows that these models are still not ready for deployment when the weather changes are significant. One option to mitigate this problem is to use data augmentation, but the problem here is that we can never generate infinite data with various kinds of weather conditions. So what we try to do is to see it from another perspective, where we see these weather conditions as adversarial examples that are traditionally visually similar, but we define them here in a rather task perceptual sense. What we say is that for a given input X and a given task, could be classification, could be regression, could be some segmentation, phi produces a perceptually similar image if the output predicted by the human is the same for both. We call that task perceptual similarity. Other such transformations could be contrast or brightness changes, blurring, rotation, sharpening, whitening, addition of noise. In the case of autonomous navigation, both for foggy and natural scene, the task would be to estimate the right steering angle, which we expect that humans would do correctly. With this definition in mind, we generate adversarial weather or the worst case scenario for each scene to help evaluate the model. For a steering prediction model, acting as a discriminator n and the adversarial transformation phi and the minimum deviation desired theta, we define a regression loss for the generator, which is what you see on the slide. Optimizing over this loss, we produce images that are perceptually similar but can cause a minimum level of deviation. From our results, we see that our method produces images with huge deviations from the original predictions. The odd columns indicate the sunny weather conditions, while the other columns show the generated foggy and rainy conditions with the respective predictions, and the difference in steering angles is significant. So throughout this work, we present a new notion of adversarial perturbations and a novel methodology for testing vision models for autonomous navigation. We hope this work can be used to better evaluate autonomous navigation models. You can find our code and website on the slides as well as on the poster. Thank you for your attention. Please stop by our poster for more discussions. Thank you.
Good afternoon. My name is Peter Roth from Graz University of Technology. Today we'll talk about a new, efficient, robust approach for room layout estimation. Room layout estimation in general describes the problem giving an image from an indoor scenario. We would like to find a constellation of the room, meaning we have different walls, we have the ceiling, we have the floor, and then we would like to estimate exactly how the room looks like. This is done, as can be seen here, using these key points, which is described by the edges, which is describing the differences and the edges between different room elements. Typically, these key points estimated directly, which is not very efficient and not very robust. Thus, in our case, we are addressing the whole problem by using some kind of media presentation to come to a better and more robust solution. This is shown over there. The main idea is now that we're having this different kind of room types, which is finally described by the number of walls, which is 1, 2, and 3. These typical types are finally grouped together, and then we're learning a CNN for two purposes. The first is, as we heard before, to run a semantic segmentation and then to extract these key points. This is shown here on the left side. So once during the inference we're getting an image, then we're estimating the segmentation of the image, and then the next step from this segmentation we can extract the key points. Having these key points, we're getting the room layout, which is shown here by this kind of black boxes, and from this room layout we can then render once again images showing this kind of elements, which is then compared to the segmentation, which is finally giving us the best hypothesis. Here I would like to show you some qualitative results. On the left side you can see the original input images, including the ground roof, and then the three following columns, they are shown the segmentation results, including also the estimated key points. The main point here, what you hopefully can see, is that in this way the segmentation results corresponds quite nice to the original input image, which is then also shown on the results which is shown on the right side. One point which is very important here is even though if you have very complex room layouts, this approach is working very nicely. This can also be seen from the quantitative results, where we did experiments on 3 different data sets. Where it can be seen that for different metrics like pixel errors or the key point errors, we're getting quite competitive results compared to the state of the art. And the other point which is important, this can be done very efficiently in terms of computational effort. In this way, if you're interested in more details, we'd be happy to welcome you at our poster. Thank you very much.
Hi, I'm Xin from University of Delaware. I'm going to present graph neural networks for image understanding based on multiple cues. So when you have a task which is very complicated, for example, understanding the overall emotional state of a group of people in the image, multiple cues, including faces, human bodies, and objects are also always used. So we propose a graph neural network to better aggregate information from those cues, and which can be seen as a generalization of RNNs from sequential to graph data. So so here is an example how to form a complete graph from an image. You have different cues, including faces, objects, and human bodies. We use different deep learning models to extract features from those cues, and then each feature can be considered as a node. And the complete graph is formed by using all those nodes connecting all those edges. So this is the illustration of a graph with 3 types of nodes, where each tab has only one node. So since these tabs are extracted from different deep learning features, they are models. They are of different lengths. So we first propose to use feature length conversion layer to convert all these features into the same length, and then we use a GRU to iteratively update those hidden features based on the neighbors. So more specifically, the features are used as the hidden state of the initial hidden state of the GRU, and the input is aggregation of those neighbors. So we also propose a fully connected layer and a softmax layer at the end to predict the class label. Also, we proposed a new graph, a group level emotion recognition data set, which all those samples actually collected from internet with different dimensions, and compared to other existing databases, we have more samples, and here are some samples shown there. And we conduct extensive experiments on the different data sets, including this new data set called Group Emo W, and our method with GNN using faces, objects, and the whole image achieves the highest performance compared to some baseline models using CNN, GRU, LSTM, and also we conduct on another famous group level emotion recognition data set and event recognition data set. So more details can be discussed in the poster section. Thank you so much.
Jenny from Scene University. Today, I want to talk about global context reasoning for semantic segmentation of 3D point clouds. Given an input of 3D point clouds, semantic segmentation is a problem which we have to predict per point semantic labels. We analyzed the existing point cloud segmentation network, PointNet++ and PointCon. From network structure, we found they are encoder-decoder structures. Information is limited by the number of network layers due to limited computing power. It tends to lose global information. From visualization results, some categories usually confuse with others. For example, window and board, door and wall. To distinguish these confusing categories, it is necessary to learn discriminative feature. So in order to capture global long-range dependencies, we proposed the Point Global Context Reasoning Module, namely Point GCR. Our method is shown above. Given a point cloud, we first use an encoder-decoder network to obtain a point-wise feature map. Then our point GCR module is appended on top of the feature map to achieve accurate point cloud segmentation. The implementation detail of our point GCR module is shown above. First, node attention. We use a channel self-attention mechanism to learn point-wise feature similarity and model them into a graph representation, namely channel graph. Then we use graph convolution to perform context reasoning on channel graph. This is our visualization result. We can see that the categories are no longer confused and the accuracy is improved. We inserted the point GCR module in PointNet++, 3D.com and DGCNN and tested the semantic results on segmentation results on the S3DIS dataset. It is obvious that the accuracy of MIOU is improved 4.34%. This is the test result on semantic 3D dataset. There are experiments on the ScanNet dataset and the comparison of network parameters and model sizes before and after adding point GCR module. Thank you for your attention.
This is Seung-han from KAIST in South Korea. Our paper name is Combinational Class Activation Maps for Weakly Supervised Object Localization. Object localization is to classify objects and identify their locations accurately. To reduce annotation costs, weakly supervised learning has been attended, and weakly supervised object localization aims to identify both class labels and locations of objects by using only image level labels. The pioneering work is class activation maps. CAM can highlight exactly which regions of an image are important for discrimination. But this method localizes the most discriminative parts, not the whole of the object. So many researchers try to solve this problem. There are two directions to solve this problem. First, they erase some parts and find other parts of the objects. Second, they find relative parts with the most discriminative parts. But they also have some limitations like highlighting background and classification degradation. To solve these problems, we highlight relevant parts of the object as many as possible by using spatial relationships, then we suppress the background regions by post-processing. We propose a novel method named Combinational Class Activation Maps. All works for weakly supervised methods use only the activation maps corresponding to the class label. Through empirical studies, a linear combination of class activation maps has an excellent capability for suppressing background regions. Therefore, we exploit all activation maps from the highest to the lowest probability classes and using various combinational functions. Moreover, we use non-local modules to find relevant parts of the most discriminative parts, as many as possible. These are the qualitative object localization results on ImageNet, and these are the qualitative object localization results on CUB dataset. They are quantitative object localization results and ablation studies in a poster session. These are our conclusion. We first adapt non-local modules to WSOL for long-range dependencies and use a linear combination of class activation maps to suppress background regions. Moreover, CCAM is a post-processing technique which can be applied to any WSOL networks, and CCAM can be exploited not only in weakly supervised object localization, but also in weakly supervised semantic segmentation. This work was approved by IITP and MSIT. Thank you for listening.
Hello everybody, my name is Andres Mafla. I'm a PhD student in Autonomous University of Barcelona. And in this task, we perform fine-grained image classification and retrieval by leveraging text information within an image. So as we know, text contains rich semantics, which have to be exploited towards a fully understanding of an image. So as we can see, we cannot perform classification or retrieval if we don't read the text. So basically, we want to leverage these semantic features, and actually, we have to acknowledge the importance of them towards other computer vision domains. So in this work, we use a PHOC, which is a pyramidal histogram of characters. It's comprised by a histogram of characters per word level. So we obtain a rich compact vector, and we use a single-shot syntax retrieval model to extract them to basically obtain a global textual descriptor. Okay. In this work as well, we use the PHOCs sorted by confidence of the detection, and those serve as input to a pre-trained Gaussian mixture model. This Gaussian mixture model contains and groups words according to the morphology of it rather than the semantics. So we exploit this subspace learned into our pipeline, which basically uses these peacocks plus the pre-trained Gaussian mixture model to construct a Fisher vector, which describes the textual information contained in the image. And we use visual attention along textual feature attention to finally perform the classification task. In our work, we also realized and we explored some fusion methods such as block, mutant, MLB, and other compact pooling methods. We evaluate our data sets within different OCRs and with different words embeddings. So also we evaluate the importance of textual features. We can see clearly on the table that the peacock and the peacock plus the Fisher vector pretty much surpasses every other embedding mechanism. We achieve a state-of-the-art into the classification task, and the query by example image retrieval will compare to other state-of-the-art approaches. We can see some qualitative results. It's quite evident that text is pretty much the only way to understand this image, and by exploiting the morphology rather than the semantics give us quite good results. Also, we can see that the learned space, whenever we perform a query, we don't have only images with text, but also with visual features. So this tells us that the learned space learns to fuse these features appropriately. So thank you. See you at the poster session.
Hi, I'm Bhavan, and I'll be explaining about our work, iterative and adaptive sampling, with spatial attention for black box model explanations. And this work was carried out in collaboration with Chen at Kitware. And this is just an overview of what interpretable AI does in a basic sense. So you have to explain why something is done, and you explain decisions in terms of when does this, you want to establish an upper and lower bound on when this works and how much I can trust a model. But the main disadvantage of black box model explanations are their coarse saliency maps, so you're not really sure, like the problem on the right where you have a saliency map for a class snowboard for MS Coco, but you still are not sure if the person contributes or what parts of the person contributes, while the human actually thinks the snowboard is the one marked in green on the right. So we would want to design a better way to sample things, and this is also very computationally expensive because you have to sample each region and do a forward pass for each region. So this is our proposed approach. So we try to, so given an input image, we try to do a Monte Carlo sampling. So this is just a coarse sampling that starts off the process. And then once we have an initial saliency map, we try to get a spatial attention map out of feature extractors. And these are just pre-trained feature extractors. And these basically look for edge informations in the picture. And we try to restrict the saliency maps inside the edge information by combining them and obtaining an adjusted saliency map. And these adjusted saliency maps are further thresholded to select regions of sampling for the further stages. So you basically do not have to sample each region of the image. And this is a deeper view into what we are using to generate the spatial attention. So we take a feature map that's a HWC, and then we basically obtain an affinity matrix, and then you want to convert it into probabilities, and then you have to weight these regions that you obtain in the initial saliency map and select regions that you would like to see. So this is more of a hierarchical concept selection, and this helps assist in that. And this process is continued iteratively till there is no change in the maps. And these are some results comparing previous black box approaches. And qualitatively, you can see that our maps are much more localized, and there's less ambiguity in what is causing the activation. And we also evaluate it at a pixel level because we want to make sure that there's more information enclosed in each pixel rather than an image level, because the image level, when you have an object that's too small, it's not weighted, or it's more of an overweighted because it's a harder problem, and you don't evaluate it, and you don't create a fair evaluation. And this is across iterations. You can see the maps improve and converge on the object that we are interested in. And these are classes for kite and spoon and mouse, and you can see the iterations progress on the bottom, where k is the number of iterations, and we go from 5 to 25, and this keeps happening till there's less changes. Thank you.
Good afternoon, everyone. My name is François Pless, and I will present our paper prepared at CEALIST and École des Ponts Paris-Tech, titled Focusing Visual Relation Detection on Relevant Relations with Prior Potentials. The task of visual relation detection consists in extracting a scene graph from an input image. A scene graph is a directed graph where nodes in red represent the detected objects in the image and are labeled with the corresponding classes. The edges in green represent the relations between these objects and are labeled with relation classes, which can be spatial relations, actions, or comparisons. The issue we aim to tackle here is the fact that existing models tend to only predict the most frequent relation when given a high number of objects. This is due to a phenomenon called reporting bias, as well as the high imbalance of examples in visual genome, which is a commonly studied visual relation detection dataset. This results in models which overlook the rarer relations in the objects. For example, person walking dog here in this image. These uncommon relations bring more information content, and then they can help differentiate between two images containing similar sets of objects, which is important for applications such as image retrieval. However, this issue is not highlighted by the commonly used metrics and datasets, which is why we proposed a new split of visual genome, which we called visual R matters for relation matters. This split has been constructed using the same set of relation as VGIMP on the left, the most studied split of visual genome. The two bar charts show the distributions of relation for the most frequent pairs of object categories for both splits, and each color in the charts represents a different relation class. We constructed VGA R matters on the right to have a more evenly distributed set of relation for each pairs, so as to penalize which models predict the most frequent relation given a pair of objects. Finally, we proposed a new approach that focuses relation detections on the most relevant object pairs of the image. The example shown here illustrates that it is able to select relevant objects and thus propose a set of likely relations, increasing the recall of the uncommon classes. This graph shows that our model in red performs much better on the rarer classes, which are on the right of the graph, than the state-of-the-art, while keeping a high recall for the most common ones on the left. And these summarized results show a significantly higher performance on both splits when compared to the state-of-the-art approaches. Thank you for your attention, and for further detail, please meet me at poster number 17.
Good afternoon, my name is Fabio Pizzati and I'm here to present a paper, Domain Bridge for Unpaired Image-to-Image Translation and Unpaired Domain Adaptation. In this work, we tackle the problem of perception in adverse weather that is now challenging because of the lack of data. As many others, we use domain adaptation to benefit from labeled data in clear weather. Unfortunately, if the domains are far away from each other, traditional methods may fail. Many of those methods use both an image-to-image translation network and an offline self-supervised learning strategy based on pseudo-label to align source and target domain distributions. We extend the pipeline proposed with three contributions. In the unpaired image-to-image translation field, we introduced Domain Bridge, that is an automatic web crawling strategy used to get more realistic images and stabilize the training. In UDA, we propose a GAN-based data augmentation strategy called online multimodal style sampling and a novel self-supervised weighted pseudo-label strategy that can be used online. The domain bridge is based on the assumption that given a source and a target dataset, we could identify two different domain shifts, one related to the weather conditions and the other related to the acquisition settings, like the camera or the city. The eye-to-eye GAN tries to learn both, but if the domains are far, the training ignores less evident features or it is unstable. To solve this, we select from YouTube two datasets acquired with the same acquisition settings, but in the weather conditions of our source and target domain, and we join the original and the web-crawled datasets. In this, we are globally reducing the domain shift, but we keep constant the one related to the weather. This ultimately results in a better and a more stable eye-to-eye translation. So here we present some results obtained with the domain bridge, and reducing the domain shift unrelated to the weather, our method is actually able to generate more weather-based feature as weather drops on the windshield. For the sake of time, we are going to discuss only our second major contributions for UDA, that is weighted pseudo-labels. So pseudo-labels is a widely used UDA strategy where unlabeled images of the target domain are processed by the segmentation network. Then the prediction is assumed to be correct on pixels with highest confidence that are used as labels. This is typically regulated by fixed thresholds that can be obtained using ablation studies or dataset analysis. In our version, we instead learn an optimal threshold during training using two losses, a weighted cross-entropy loss, where the weights depend on the threshold, and the balancing loss. So here we have some results on the UDA that demonstrate the effectiveness of all our contributions, and we perform on par with the most recent state-of-the-art, but with a much simpler pipeline. So thanks for your attention, and for questions, come at the poster. Thanks.
Good afternoon to everyone. I am Vinay. I am presenting a network-to-network pruning approach for the deep model compression. So the objective is, there is a two kind of deep model compression approach. One is the filter pruning, one is the connection pruning. In this model, we are proposing a filter pruning approach. And it is very simple model, but it is interesting to see that how we can prune a one network with the help of another network. And with this help of this network-to-network pruning approach, we can get the high pruning ratio. Most of the previous approach, they are modeling the filter importance, and these model, they are unable to model the layer importance. In this approach, we model the layer importance also, and the previous approach, they are unable to prune the complex architecture, for example, the skip connection in the ResNet architecture. And in our approach, we propose an end-to-end filter pruning approach that model the layer importance as well as filter importance. Also, we are able to prune the complex architecture. So this is the proposed architecture. Here we have one main network, one is the multitask network or pruner network. This pruner network gives weight to the each filter in the main network, and we have to optimize this joint network such that most of the weight to the filter are zero without degrading the accuracy in the main network. And once we can make the weight to the filter to zero, so we can easily remove this filter from the main network and we can get the compressed model. Here the number of multitask is equal to the number of layer in the main network, and in each multitask the number of node is equal to the number of filter in the main network. The right hand side shows the illustration of particular layer and gives the final pruned model. Using this model, we can get the high pruning ratio on the ResNet 56 architecture and the CFR10 dataset, and we can see here we have the 61% compression with the minimal drop in the accuracy compared to the baseline. Also, we can see that on the ResNet 50 architecture over the ImageNet dataset, if we prune this 60% and we had the better result compared to the baseline, so it helps to remove the overfitting. Also, if we go the high pruning rate and we have the high pruning ratio with only significant drop in the accuracy compared very close to the baseline approach. So in this approach, we propose a filter pruning approach for the deep model compression, and that is end-to-end. It also models the layer importance as well as filter importance. Thank you.